Nuclear fusion, the same process that powers the sun, is often called the holy grail of energy. But after decades of research and billions of dollars, why haven't we cracked the code? Why is nuclear fusion still out of our reach? Stick around, because what we're about to uncover might surprise you. Nuclear fusion has the potential to revolutionize energy, offering an almost limitless, clean power source. Yet, despite the hype, we're still far from building a commercial fusion reactor. In this video, we'll dive deep into the science of nuclear fusion, the promises, the pitfalls, and the very real challenges standing in the way of this breakthrough technology. Whether you're a science enthusiast or just curious about how our universe works, this topic is crucial for understanding our energy future. So, what's the big deal with nuclear fusion and why is it so hard to achieve? Fusion is the process where two light atomic nuclei combine to form a heavier nucleus, releasing a tremendous amount of energy. It's what powers the stars, including our sun, which generates energy by fusing hydrogen into helium under extreme temperatures and pressures. But recreating these conditions on Earth is a different story altogether. The temperature needed to ignite fusion? Over 100 million degrees Celsius. To put it in perspective, that's hotter than the core of the sun. Keeping that kind of heat confined without things melting or flying apart is where the real challenge begins. What makes fusion so appealing? Nuclear fusion promises a lot. Clean energy, no greenhouse gases, and almost no long-lasting radioactive waste compared to nuclear fission, the type of reaction used in today's nuclear power plants. Plus, the fuel for fusion, hydrogen isotopes like deuterium and tritium, is abundant. Deuterium can be extracted from seawater, and tritium can be bred in reactors. This means we wouldn't have to worry about running out of fuel anytime soon. Sounds like a dream, right? But turning this dream into reality is a matter of incredible complexity and scientific innovation. The allure of fusion power is compelling, especially in a world grappling with climate change and the need for sustainable energy sources. Imagine a future where energy is so abundant and cheap that it could drastically reduce our dependence on fossil fuels. This future could help mitigate climate change while providing energy security to a growing global population. The science behind fusion works by smashing atomic nuclei together at incredibly high speeds, overcoming the natural repulsion between positively charged particles. When these nuclei collide, they release energy. But here's the catch: getting them to collide requires insane amounts of heat and pressure, conditions that are incredibly difficult to maintain in a controlled environment. In stars, gravity does all the work of holding the fuel together. The immense gravitational pull in the core of stars creates the necessary conditions for fusion to occur naturally. But on Earth, we don't have that luxury. We have to rely on devices like tokamaks and stellarators, which use powerful magnetic fields to contain the superheated plasma where fusion occurs. These reactors create a magnetic field strong enough to hold plasma in place without coming into contact with the walls of the reactor, which would cause it to cool and stop the reaction. However, even with these advanced machines, maintaining stable plasma long enough to produce more energy than we put in is the core issue. The energy input versus output is still heavily skewed in the wrong direction, and that leads us to the next point. Why hasn't fusion worked yet? One of the biggest hurdles for nuclear fusion is that we've yet to achieve a state called ignition, where the energy produced by fusion reactions exceeds the energy used to start and sustain them. So far, every experiment has required more energy to heat the plasma than the fusion reactions have generated. The most successful fusion experiments, like the ones at the International Thermonuclear Experimental Reactor, ITER, and the National Ignition Facility, NIF, have shown progress but haven't reached the critical point of sustained fusion. One key challenge is plasma confinement. The plasma is incredibly hot and unstable. Scientists must develop techniques to stabilize the plasma long enough for fusion to occur. The use of magnetic fields is essential, but these fields must be incredibly strong and precise. Any fluctuation in the magnetic field can lead to the plasma escaping containment, which stops the reaction immediately. Furthermore, researchers are looking into alternative methods of confinement. One promising approach is inertial confinement, where powerful lasers compress fuel pellets to achieve the necessary conditions for fusion. This method has shown some success in experiments, but it's still a long way from being a viable energy source. Fusion's cost problem. And then there's the money issue. Fusion research is expensive, like really expensive. Projects like ITER have budgets running into the tens of billions of dollars, and they've faced numerous delays and cost overruns. Fusion reactors require materials that can withstand extreme conditions, and developing those materials is costly. Add to that the price of building the infrastructure needed to house and run a fusion reactor, and you begin to see why it's been such a financial strain. Technological challenges. Let's talk about tokamaks. These donut-shaped reactors are our best bet for achieving fusion, but they come with their own set of problems. First, the magnetic fields used to contain the plasma have to be incredibly strong and stable. Any fluctuation, and the plasma can escape, causing the reaction to stop. This instability is one of the major obstacles scientists are working to overcome. Additionally, materials that can handle constant exposure to high-energy neutrons are still in development. Neutrons released in the fusion process can damage reactor components over time, making maintenance and longevity another hurdle. Despite all these challenges, why are scientists still so confident that nuclear fusion is the future of energy? The answer lies in the progress we've made. ITER is set to achieve first plasma by 2025, and while it won't generate electricity, it's a critical step in proving the feasibility of fusion power. Meanwhile, private companies are getting involved, like Commonwealth Fusion Systems and TAE Technologies, who claim to have faster, cheaper paths to fusion. These companies are working on innovative designs that may solve some of the key problems holding fusion back. However, the real question remains: will fusion come in time to help combat climate change? The world needs clean energy now, and fusion, even in its best case scenario, is still decades away from being a commercially viable solution. So, what's the takeaway here? Nuclear fusion holds incredible promise. Clean, nearly limitless energy with no carbon emissions or long-lived radioactive waste. But the road to making it a reality is long, expensive, and filled with technical challenges. Despite all the hurdles, the dream of harnessing the power of the stars on Earth continues to drive scientists forward. Will we crack the code? Only time will tell. If you want to stay updated on the future of fusion energy, hit subscribe and like the video.